Hello and welcome to my presentation of the work Efficient Future Learning for Multi-Label Classification of Scientific Documents with many classes. I would like to start this presentation with the motivation of our work, which is found within the scientific literature, which grows exponentially over the last few decades and years, as you can see here on the figure on the left, on the number of publications that are published on the ACL ontology. However, to be searchable and also accessible to researchers, policymakers, the public, and so on, scientific literature has to be managed and should be categorized in digital libraries. However, this is a significant challenge due to the huge volume of documents that do exist and get published every year, and also the variety of topics they cover. And in addition to the broad spectrum of possible research topics that can be served as classification categories, scientific documents also cannot often only be assigned to one class due to their interdisciplinary character. So consequently, the automatic categorization of scientific documents has to be approached as a multi-label classification problem over very large label spaces, which is the task we try to solve here. There are certain challenges that we have to face during our work. One challenge is data scarcity. So labeling scientific documents is very costly and also time-consuming, and often large label data sets are just unavailable, especially if there are new or emerging fields that have to be categorized. Also, there's the multi-label nature of the documents. As I mentioned already, many documents cover interdisciplinary topics, which also requires assigning multiple categories to one document, which makes the data annotation more complex, as well as the classification problem. Finally, as I already mentioned, we have very large-scale label spaces, which just mean that the list of possible scientific topics that could be assigned to one document is very large. So we're talking about dozens to hundreds of possible classes, making the classification problem especially challenging. And this also means we cannot just use an LLM and zero-shot or few-shot prompted to do the classification for us, because all the possible label or class descriptions do not even fit into the context window of an LLM. Therefore, we have to find another solution. And one possible solution is FusionSend, which we propose in this paper, which is a method that leverages fused sentence embedding models for robust few-shot multi-label classification. Before I introduce our approach, I want to talk a bit about the background that is needed to understand this work. Firstly, few-shot classification is an approach to train models with only a small number of labeled examples per class, let's say 2, 4, or 8 examples per class, and this reduces the cost and also the time needed for data annotation and allows to quickly adapt models to new domains or tasks. There are a lot of different approaches out there for few-shot classification, which I do not explain in detail now, but most of those approaches have in common that they require very large models in the billion parameter sizes, and also they require some kind of prompt engineering, which makes the output not very stable and robust. In addition to those approaches, there also exist the sentence embedding model fine-tuning approaches for few-shot classification, which was essentially introduced in 2022 by Tunstall et al. And they show that this few-shot classification can be approached in a two-step process. And in the first step, A sentence embedding model is fine-tuned in a contrastive manner by sampling positive and negative sentence pairs from few-shot labeled examples. And then in the second step, the fine-tuned sentence embedding model is frozen to encode the few-shot examples, and the resulting embeddings are then used as input features to train a simple logistic regression classifier as the model had. And this has shown to perform very well and also has two advantages. One of it is that it requires significantly smaller model sizes, so in the million parameter scale, and it also does not require any prompts or instructions, which makes the model very robust to different types of inputs. Another thing I want to talk about here is model fusion, which is important in the next slide. So model fusion basically means that we integrate the capabilities of different models into one model or one output to have an overall better prediction performance. And there are basically two approaches to do this. One approach is ensembling, where we take the output from one or two or more models and combine those outputs, usually with like averaging the outputs or doing some majority voting to improve the prediction performance. And the other approach, which is something we take a closer look at, is weight or model merging, where we merge the weights or parameters from two or more models into one, and then yield one model from that that shows enhanced prediction performance. So in the next slide, given this background, I would like to introduce our FusionCent approach, which you can see illustrated here. Specifically, you can see the illustration of the training process of our approach here, which is divided into 3 steps. In the first step, we fine-tune 2 different sentence embedding models from the same pre-trained language models with the parameters θ1 and θ2 respectively. And then θ1 is fine-tuned on pairs of training sentences using a cosine similarity loss. And specifically from the few-shot training examples, instances of the same class are selected as positive examples, and instances from different classes are selected as negative pairs. The model with θ2 parameters is then fine-tuned on pairs of training sentences and their corresponding labeled texts using a contrastive loss. And specifically, this means we sample positive pairs from training instances and the label texts of the classes that are assigned to those instances, and negative pairs consist of training instances and label texts from different classes. So to explain label texts maybe a bit, those can be just simple class or label names as you find it in any text classification dataset, or even more extensive or detailed descriptions that semantically describe a class or label. Could be then derived from a domain expert, for example. In the second step of our training process, we then merge the parameter sets θ1 and θ2 into model θ3 using slurp merging, the slurp algorithm, which then results in a model that is derived from the same architecture as the base pre-trained language model. And in the third and final step, we then freeze the parameters in this model θ3 to embed the training sentences from the few-shot examples, which are then used as input features to train our logistic regression classification head on top. So as for the experimental setup, we use 3 different datasets to evaluate our model. One dataset is an archive multi-label classification dataset, which we constructed during the course of our work, which includes more than 200,000 scientific documents categorized into 130 different classes based on the archive category taxonomy. Second data set is a Sci-HTC, which consists of computer science papers categorized in 62 different classes. And the third data set is an NLP taxonomy classification data set consisting of NLP-related papers with 82 different classes. In addition, we also examine different baselines. The first baseline is a standard fine-tuned baseline where we have a default encoder-only transformer model, which is fine-tuned then for text classification, but no special optimization for the few-shot classification case. Then we use a set-fit model as proposed by Tunstall, where we have one sentence embedding model that is fine-tuned on pairs of training sentences using the cosine similarity loss. Further, we use a label embedding model approach where we use also one sentence embedding model, but this one is then fine-tuned using few-shot examples and their corresponding label tags in a contrastive learning approach. In addition, we try to combine the training approaches of set-fit and label embedding, the label embedding approach in one model, training one model. So one sentence embedding model is first fine-tuned with the set-fit approach, and then the training is continued with the label embedding approach, but on the same model. We also experiment with reversing the order. So we again train one sentence embedding model, but firstly fine-tune with the label embedding approach and then continue training with the set-fit approach. Finally, we try fusion send as proposed in the earlier slide, where we have two different sentence embedding models that we then fuse into one model body.
We need to wrap up in 2 minutes.
Yeah, I'll make it fast. Looking at the results, we can see different things. First of all, the fine-tuned model is not able to learn very well with the few training examples. We also see that on average, fusion send outperforms set-fit by 6 F1 points. However, we do not see any significant performance increase when trying to combine both training approaches into one model. So we conclude that longer training on one model is not necessarily beneficial because one sentence embedding model tends to forget the previously learned things. However, like training then two separate sentence embedding models with different approaches and then merging their parameters allows to contain their respective knowledge and to complement each other and yield in better downstream performance. So as for the conclusion of our work, I would like to reiterate on our contributions, which is for one, the data set we constructed for classification, and also our fusion send model that offers a simple and prompt-free approach for classification with many classes in the few-shot setting. Our model outperforms a strong set-fit baseline, and fusion send also works with very small models. So in this case, we used a 110 million parameter size model, and which is very computationally efficient during inference. For future work, we would like to look into different model merging techniques and would like to further investigate the impact of label text variations. Thank you for your attention.